All right, we're going to go over all single bonds. So that means you have just enough electrons to connect to everything and possibly have lone pairs off the middle. So we're going to go through the steps as usual. So first you just count your total number of valence electron. That's going to be 4 plus 4 because hydrogen's group 1, carbon's group 4. So 4 times 1 is where you got the 4 for hydrogen, even though each individual one has one valence electron. So that gives me a total of 8 valence electrons. Drawing the Lewis structure, remember middle. 2 dots or a line equals a connection, and you need to have one connection per outer atom. So there's 4 hydrogens, so we're going to make 1, 2, 3, 4 connections. That uses up all 8 electrons. That's 2, 4, 6, 8. Remember, hydrogen only wants to have a connection. You don't put lone pairs off. You don't do double bonds or anything like that. So we're done with CH4. Shape, because you have 1, 2, 3, 4 domains, that's going to give you a tetrahedral structure. It's easy to try to shortcut this, but tetra, don't do that. Put the complete name. That's the most appropriate thing to do. All right, polarity. You have dipole moments on each C and H, but because they're opposite each other, they cancel. So the dipoles off of this CH and this CH would cancel. CH in particular, if you remember, doesn't have any polarity because the electronegativity is so similar, we tend to call it nonpolar. So if you just see it C and H only, you'll just call it nonpolar, you're done, there's nothing else to do. But just to give you context for what if there was some polarity, because these are symmetrical, these H's cancel out these H's, these cancel these, you have what's called a nonpolar structure. So that'd be nonpolar. IMFs, LDF is automatic London dispersion forces. Because it's nonpolar, there's no dipole-dipole. There is hydrogen, but remember, hydrogen needs either F, O, or N in order to be considered hydrogen bonding, and H is not bonding to any of these 3 elements because they don't exist here. So as a result, this doesn't have hydrogen bonding, so just LDF, you're done. H2O, 6 plus 2 gives you 8. Again, O in the middle, whatever you have less of, always goes in the middle. Connect your H's. I'm going to do it visually. You don't have to do it this way. I just do it because it is technically a bent structure, and you'll get to that. But if you just put it opposite, it's fine. You have 2 sets of lone pairs left because you only used 4, right? So you have 4 left. Now look at the middle. See, the middle only has 2, 4, and wants 8. So I'm going to give it 2 more. As a result of that, we have a bent structure. And as you know, from bent structures, they're going to be typically polar. Can't think of an example where it's non-polar, but in this situation, the reason it's polar and so easy to identify as polar, lone pairs. Remember, anytime you have a lone pair, unless it's a square planar structure, you're going to automatically have a polar structure available because of the lone pairs. That's just the way it works. So it's going to be polar. So LDF, standard, that goes for everything, right? Dipole-dipole. Once again, I know it's easy to put DD. I mean, I did LDF for this because I don't spell London dispersion forces, but you do want to spell it out. Is there hydrogen bonding? Yes, it is, because O is there. And remember, O is an example of something that H can be attached to. We have hydrogen bonding. So H bond is there. I'm going to put H bond instead of hydrogen bond. All right, PB3L3, that's right, PBr3. You have a total of 7 times 3, that's 21. This is group 5 plus 5, 26 electrons. So 26 goes here. P in the middle, because it's whatever you have less of. Br, that's one connection. Br, another connection. There's your last Br, the last final connection. 6 electrons used, you have 20 left. Remember, outside in, you're going to make sure the outside is 8 first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's 24 electrons we used up so far, right? So we have 2 left. What do we do with that? You look at the middle first, realize it only has 6, but it wants 8, and then just stick off the lone pair off the middle. Remember, if you have a lone pair, always goes off the middle. Or if you have extras, I should say, you always put it off the middle. Never, ever do a double or triple bond when you have extra electron. That's a big, big no-no. So don't do that. All right, anyway, so structure, trigonopyramidal. Why? Because it has 3 bonded pairs and 1 lone pair. 3 plus 1 is always going to be trigonopyramidal. Excuse me. So polarity, lone pair. There's your clue. Have a nice day. All right, LDF automatically. Dipole, because you're polar. Anytime you're polar, you have dipole. They go hand in hand. Don't forget that. All right, CF4. 7 times 4 is 28. Plus 4 more gives me 32 electrons. Carbon in the middle. Remember, if carbon's involved, it's always the middle. F. So he's a total of 8 electrons. That means 24 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There's all your electrons. You're done with all your electrons. So now you just look at them all and make sure it has 8. 2, 4, 6, 8. It does. So this is going to be definitely going to be tetrahedral structure. And you're done with the Lewis structure. And that's because you have 4 domains, right? 1, 2, 3, 4. 4 domains that are all bonded. Always tetrahedral. Now, as far as the polarity is concerned, you have a dipole moment going this way, right? Because fluorine's more electronegative. Dipole moment go that way. Dipole moment going this way. All these arrows. You don't have to really draw the arrows. You can look at this and say, oh, it's symmetrical when you're done. Polarities cancel. Polarities cancel. So it's symmetrical, which means you are non-polar. If you're non-polar, that's all you have is LDF. If you have non-polar, your thing is going to be LDF every time. Now, if you have ammonium, you actually would have LDF and hydrogen bonding. It's a rare exception where a non-polar substance has something beyond LDF, but it's not typical. Usually LDF and non-polar, and that's it. There's no other two IMFs to worry about. All right, BF3. You have a total of 3 plus 21. That's 24 electrons. So 24 goes here. B in the middle. F. So we use the total of 6, 18 left, 2, 4, 6, 8, 10, 12, 14, 16, 18. There's all your electrons. Now, you look at the middle, you're like, oh, it doesn't have 8. Then you remember that it's got an exception. Boron does not want to have more than 6. You are done. Do not do double bonds, not do anything cute. You are done with boron. So this is the complete Lewis structure. And because you have 1, 2, 3 bonded domains, you're going to be considered trigonal planar. All right, polarity. So a little quirk, trigonal planar structures are non-polar. Now you're looking at this and you're like, wait a second, there's 3. How do you cancel? That's symmetrical. You have to think 3-dimensionally. And when you get to the point where you're drawing or building Lewis structure, you'll see a little bit better. But for now, just remember that if it's trigonal planar, you're going to be non-polar, provided all 3 of the outside elements are the same element, because they cancel out. If this was like a Cl here and 2 Fs, this would not work out, because the Cl would not be able to cancel out the effect of the fluorines. It has to be the same element on the outside to cancel each other out. Like if you have F and F, great. If you put F and Cl, no, not good. Same thing with this. If I change this F to an I, 2 different elements, they can't cancel each other out. Yes, the structure is symmetrical, but the polarity does not cancel because you don't have the same electronegativities for the outside elements. So keep that in mind. Anyway, so non-polar, so that means LDF, and we're done. Nothing else you need to do there. NH3, you have a total of 5 plus 3 gives you 8. 8 goes here, and in the middle, H, 2, 4, 6. You have 2 left. What do? You know you don't do double bonds with H. You don't do lone pairs with H. So off the middle. Have a nice day. So structure's done. You have a lone pair, so keep that in mind. So 3 bonded, 1 lone is always going to be trigonal. Pyramidal. Right? 3 plus 1 is always going to be that. So keep that in mind. Just like 2 plus 2, 2 bonded, 2 lone is always going to be bent. 2 plus 1 is also bent too, remember? 2 bonded, 1 lone pair, that is. So anyway, so for this one, polarity, well, we have a lone pair, so guess what? Automatically polar. You are done with that part. LDF, you notice all these have LDF. That's not a coincidence. Everything has LDF, so make sure you put LDF first. Even if you don't do the Lewis structure, put LDF, because that's the first thing everything's going to have. All right, secondary, so because it's polar, you have dipole. And because you have H bonded to one of the fun molecules, which in this case is N, you also have H bond. So it has all 3. All right, so that's how you draw Lewis structures with things that have all single bonds.